Welcome to Project R2-ARC. R2-ARC is a companion that will serve to enhance the quality of life for its users by having a voice assistant, life alert, smoke and gas detector, and a companion app. So let's meet the team. May you introduce yourself, please?
I'm Kevin Martinez. I'm in charge of the machine vision.
Oh, that's it. Okay. May you introduce yourself?
I'm Jesus Perez. I'm in charge of the motors and SPI communication between the main SBC and the Team 4C.
And you, sir?
I'm Shane Lobsinger, and I'm in charge of the iOS app development.
Hi, I'm Gracia Francisco. I'm in charge of the gas sensor programming and printing the R2-ARC body.
And I'm Michelle Tran, and I'm in charge of the voice assistant as well as the power system of our project.
Kevin here. So let's just dive into the demo overview. For those who are new or need a refresher, a couple months ago, Jesus demonstrated his motor system using a TM4C MCU with a couple of motors. Now for demo 2, Michelle and Gracia created a voice system gas and smoke sensor, demonstrated that with the text and an alert. Now for demo 3, we're going to be presenting machine vision. Not only that, we did a little more unrelated to the machine vision though. So what we're looking at here is a high level of what we implemented for this demonstration. Now, we have a main file that's using a bunch of other modules. So let's go ahead and talk about our Bluetooth low energy service that we implemented. We didn't think we'd get this far because implementing Bluetooth low energy on iOS is quite difficult because we're using Swift and we're communicating across a Linux-based system. And simply, there weren't too many resources out there implementing these two technologies. We did come across PyBleno, a JavaScript translated library into Python, which allows us to create a service and a characteristic. Now, Bluetooth Low Energy is quite different and comes with some difficulties setting up as well. So Bluetooth Low Energy is really efficient wattage-wise. Our devices advertise a specific ID, a service ID, and a characteristic ID. And once one another recognize each other, it forms a connection. However, because how Bluetooth Low Energy communicates, we can't send too much data around. So we created a characteristic that stores values, specifically characters, from the iOS device onto the Linux device, which is our Raspberry Pi 5. Once I had a basic demo of this configured, I was able to easily, and with the help of Shane, implement it into our main app due to the structure of our code, which is really well organized and follows significant programming principles. You'll see off to the side the differences between the bare bone Bluetooth Low Energy app on the right and our fully implemented app on the left. Right now, it'll show there's no connections or Bluetooth device available, and it will be grayed out as well to indicate that. However, we'll see how it looks like later down the line in our demo. So we use this Bluetooth Low Energy Python file in our main file, and this is how it works on a simple level. While the program is not interrupted, receive an iOS character command. Then transmit that received character command to our motor control, which is basically our TM4C MCU we were talking about just a while ago. So here we see our motor controller communication module, and we're connected and communicating through SPI. We're using simple commands that tell it to go forward, backward, left, right, pivot right, and stop. We chose SPI because we wanted to decrease that latency as much as possible. We want our droid to do micro adjustments on the fly. And again, our Raspberry Pi is communicating with our TM4C MCU that's using the programming language C. And I'll have Jesus explain a little bit more in depth.
Hello, I will be discussing the implementation of continuous SPI communication between our Raspberry Pi and our TM4C microcontroller. Synchronous Peripheral Interface, or SPI, is a master-slave communication protocol that allows high-speed synchronous data transfer. On the hardware side, the TM4C is configured as a slave device, and our Raspberry Pi is configured as the master. And the way our program works is that our Raspberry Pi here, this one, will send data to the TM4C, and it'll send unsigned chars, and depending on what unsigned char is received, it'll do a specific motor direction. So first we need to make sure that both the master and slave clocks are the same frequency. To set the frequency on the TM4C, there's an equation that we must follow. It is system clock divided by CPS divisor times 1 plus SCR. So here is the equation, and what we did was we wanted it at 5 megahertz or 5 megabits per second of data transfer. So we did 40 divided by 8 times 1 plus SCR, and then just note this must be an even number. The crucial aspect here is the management of the select signal. So our select signal is PA3. We had to make sure that the select signal was kept low throughout the transmission of a command sequence. This setup prevents any misalignment in command sequences due to intermittent signal assertion. For our application, we initialize our clock polarity to 1, so SPO is equal to 1, and our clock phase to 1. This allows our clock polarity to be high when idle, and data is latched onto the rising edges of the. So these are the rising edges. For continuous back-to-back transfers, the select pin, this one, is held low between successive data words. So it's going to be held low. And the select line is returned to its idle high state 1 clock period after the last bit has been captured. So this setup ensures high data integrity even during continuous operations by aligning data transitions with clock stability.
So now that we understand what's going on under the hood, we could talk a little bit about our machine vision program now. We're constantly interacting with our main file, and we do use our motor controller module when we have it on autonomous mode. Specifically, we have a machine vision method called find human method that looks at a bounding box. So that's the square that surrounds an object, and uses those coordinates to guide itself to the object. Now, we are using a Google Coral TPU, and we are using an open source machine vision model they deployed. We have fine-tuned it and adjusted certain aspects to their functions to have our droid guide itself a little bit better, and so it can recognize humans a little bit better as well. We also implemented a human position, a last human position specifically, variable that caches the position side of the last human seen. And again, we're using Google Coral's open source model that uses GStreamer. Now, we're using a custom GStreamer library to obtain camera images and perform image classification and object detection on Google Coral Edge TPU. For the most part, it looks like regular GStreamer library. However, we have a couple of modified files to support the Google Coral TPU and to adjust the model a little bit for our droid's height and movement. Now, there's something I want to get into. For those of you who are new or need a refresher, 6 months ago, we were using a Google Coral TPU that is in the form factor of a USB. Now, we have transitioned to an M.2 Google Coral TPU. Now, what does this mean? We have transitioned into a much faster interface. We have gotten some insane gains from this. We have doubled our speed in inference times. So that means it's taking half the amount of time on the M.2 versus the USB Google Coral TPU. We significantly decreased latency on our machine vision implementation. However, I really want to emphasize this is really difficult to implement this. I was the first person to do this natively. I was inspired to do this as I saw people testing out the M.2 Google Coral TPU on the Raspberry Pi 5. However, they were doing it using a VM, virtual machine, and the gains weren't that significant. So I set out to do it natively. Luckily, I came across those GitHub repositories that implemented using a VM and also a video using that VM implementation drop, and was able to implement it in modifying the device tree on the Linux Debian operating system. So yeah, I had to change just the operating system to get this to work. It was a lot of trial and error. Learned a bunch about operating systems and permissions specifically, and felt very relieving when I got it to work. Now, how am I using this machine vision algorithm? Well, I'm using a follow state and command to tell our machine vision class to follow human or not. So something I want to emphasize on is creating this program required us to multi-thread, specifically because we had multiple devices, multiple technologies working in parallel. So we had a main thread, we had a Bluetooth low energy thread, technically two, and another machine vision thread. We used a bunch of flags to update one another and got it to work. Debugging was a little bit difficult because we would get vague errors about threading. Nonetheless, let's take a look at their demonstration now.
Okay, so I developed this power system with the help of one of our other classmates, and we are currently using a 14.8 volt battery with 8,000 milliamps. That is because the Raspberry Pi 5 is rated for 5 volts and 5 amps, which is a bit unusual, and the TM4C is rated for 5 volts and 3 amps. So connected to this 14.8 volt battery is a prototype PCB, and I have two large soldered power lines.
Zoom in onto that.
Covers, yeah, okay. And then I soldered on a switch to easily turn on and off. So it's these two lines, and the two buck converters are in parallel, so they both get 14.8 volts, but the output are different. So this one outputs 5 volts and 3 amps, which is needed for the TM4C. Well, actually not 5 volts, 12 volts, and enters a R2-ARC motor driver, which powers the TM4C, and then this buck converter powers on the Raspberry Pi 5, which outputs 5 volts and maximum 5 amps. So that is a complete summary of our power system.
So we set up our battery, our camera, our main board computer, our single board computer, and our TM4C that's linked to our motor system control. Now we're going to go ahead and test it out. So I'm going to go ahead and go to my computer and initialize that program. All right, so we're on the computer here now, and we're going to go ahead and connect to our single board computer, which is our Raspberry Pi 5, or VNC. All right, so we're all connected to the same network on my hotspot on my phone, and now I'm going to go ahead and enter VNC. All right, so we're in VNC now. We're going to go ahead and open up Visual Studio Code, and we could see on the left-hand side, on a high level, what's going on. We have some object-oriented programming, by the way, for our motor control, our Droid Vision, and our Bluetooth low energy service. So we're going to go ahead and open up our source folder and then run our main code, which is R2-ARC.py. And at the same time, we're going to go ahead and set up our R2-ARC app. So we can see our camera view frozen in place right now in that corner. So I'm right over here. So now we're in our mode selection, and we're going to go ahead and click on autonomous following mode. So it should pivot left by default first. So it's going to search for a person, and eventually it should reach to me. I'm going to move around for a bit. This is slow. I'm going to fast forward this bit. Yeah. So it's reached its destination. I'm going to go ahead and turn off following mode real quick. So yeah, we'll try it again. It should slowly shift towards me. So let's wait for it to actually follow me. So it got towards me, and now we're going to go ahead and turn off following mode, and we're going to go into remote control. So let's take a look at it. Let's go backward. By the way, you can see I'm holding down the button. When I let go, it turns on. Now let's go left. Let's go right. Let's go forward. And again back. So that just demonstrates our remote control and our autonomous following mode. As you can see on the terminal, we saw a couple commands. We saw the IO's BLE command character being sent from our iPhone to our main single board computer. So just for reference, it's like a computer game where you use WASD for forward, left, backward, right, and so on. So once you press W, you move forward. Once you press A, you move left. Once you press S, you move backward. Once you press D, it moves right. This adds some modularity where we can implement other controls other than our iOS app, maybe down the line. And we can see how when we're moving around or when we're autonomous following mode, we can change between states, between remote state, following state, and the idle state. That concludes our demonstration.